Determine all values of c that satisfy the conclusion of Rolle's theorem for the function f of x equals x times the square root of 200 minus x squared on the interval 2 included to 14 included. The first thing to do is to determine whether the three conditions are met for Rolle's theorem to apply. The first condition, the function f of x, which is x times the square root of 200 minus x squared, has to be continuous on the closed interval given. X times the square root of 200 minus x squared does not exist everywhere because what's inside a square root has to stay greater than or equal to 0. So 200 minus x squared has to be greater than or equal to 0. We can solve for x by subtracting 200 from both sides, so minus x squared is greater than or equal to negative 200. Now, multiply or divide by negative 1. Either way, we have to flip the inequality, and x squared is less than or equal to 200. Now we can take the square root of both sides. The square root of x squared is the absolute value of x. And that'll be less than or equal to the square root of 200. 200 is 2 times 100, and 100 is a perfect square, so it can come out of the square root as a 10. The 2 is not a perfect square and will stay in there. Since we have the absolute value of x is less than or equal to 10 times the square root of 2, x will end up between plus and minus of 10 square root of 2. For our function to be continuous, it has to be in this interval. The interval given, 2 to 14, has to be equal or smaller than the interval required. The left end point of the interval given, a 2, is definitely within that range of negative 10 root 2 to positive 10 root 2. 14, we have to look a little bit closer. 10 root 2. Root 2 is 1.414. If we times that by 10, it's 14.14. And 14 is slightly less than that. And so it is also within that interval. And so the interval of 2 to the 14 is okay. And therefore, we will be continuous on the closed interval given 2 to 14. Closed means that it includes both endpoints, indicated by the square brackets on both endpoints. Condition 1 is met. The second condition, the derivative, f prime of x. In order to find that, we may need to rewrite f of x because of the square root. Let's rewrite it as a fractional exponent, square root to the first power, 1/2 power. We have, for f of x, a product of x times 200 minus x squared to the 1/2. We will have to use the product rule. Derivative of the first, which is a 1, times the second left alone, 200 minus x squared to the 1/2, plus the first left alone, x, times the derivative of the second. Bring the power down, 1/2, leave the inside alone, 200 minus x squared. Subtract 1 from the power, I will call that 2/2, and then multiply by the derivative of the inside to complete the chain rule, minus 2x. The first term, 1 times anything, is the same thing, so we have 200 minus x squared to the 1/2. The second term, we can bring the minus 2x out with the x and the 1/2 and multiply those together. 1/2 times minus 2 is minus 2/2, or minus 1. And then the x times the x will be x squared, so we'll have minus 1 x squared, which we can write as minus x squared. The 1 is implied. Times the 200 minus x squared, that is to the 1 minus 2 negative 1/2 power. Since we have a negative exponent, we will need to rewrite that second term by moving it to the denominator to make it a positive exponent. So the derivative will equal 200 minus x squared to the 1/2. We'll leave that term alone. And then minus the second term, the x squared will stay in the numerator. It's not raised to a negative exponent, but the 200 minus x squared will need to move to the denominator to become a positive 1/2 power. The positive 1/2 power is the same thing as square root, so we can rewrite each of these to be square root. Where we see the positive 1/2 power. What we want to do with the derivative is determine if it's continuous. It's called differentiable on the open interval. In order to determine that, we will need to get this to a single fraction. So we need to produce a common denominator between the two terms here. Well, the first term doesn't have a denominator at all. The second term has as the denominator that, so we can multiply the first term by that over itself. So the first term, which is the square root of 200 minus x squared, we can multiply that by a square root of 200 minus x squared over itself. To get the common denominator, let's leave the second term alone. So that the derivative f prime of x now equals, multiplying the numerators here, square root times square root cancel each other, and that becomes 200 minus x squared. Since we're over a common denominator, we can combine it with the other numerator, which is a minus x squared, all over that common denominator of the square root of 200 minus x squared. In the numerator, we can combine the minus x squared with the other minus x squared to give minus 2x squared, all over that common denominator. Our derivative needs to be continuous. It's called differentiable on the open interval. 200 minus 2x squared divided by the square root of 200 minus x squared does not exist everywhere, because what's inside of a square root has to stay greater than or equal to 0. But because the square root is in the denominator and the square root of 0 is 0, we cannot have it be equal to 0. It has to stay greater than 0. So that 200 minus x squared has to be greater than 0. We can solve for x by subtracting 200 from both sides. Divide or multiply both sides by a negative 1, it flips the inequality. Take the square root of both sides. Square root of x squared is the absolute value of x. The square root of 200 once again becomes 10 square root of 2, and we can remove the absolute value symbols by putting between the positive and negative of that 10 square root of 2. There's the interval required for the derivative to be continuous. It's called differentiable. And once again, the interval given of 2 to 14 is contained within there because 2 is within there and 14 is still less than 10 times root 2, as established before. So it looks like everything's good here, and therefore the derivative is continuous. It's called differentiable on, and it's on the open interval, indicated by the round brackets on the endpoints, meaning that it doesn't include the endpoints because the function is never differentiable at its endpoints. So it's always on the open interval here. So condition 2 holds true. The third condition, f of the left endpoint A has to match f of the right endpoint B. In this problem, the interval is 2 to 14. The left endpoint A is 2, the right endpoint B is 14. We will need to evaluate the function at each of those endpoints. F of 2 and f of 14. F of 2 and f of 14, they will be evaluated by plugging them into f of x here. F of 2 will be 2 times the square root of 200 minus 2 squared, which will be 2 times the square root of 200 minus 4, which will be 2 times the square root of 196. And 196 is actually a perfect square. It comes out to 14. So this will be 2 times 14, which is 28. F of 14 will be 14 times the square root of 200 minus 14 squared, which will give 14 times the square root of 200 minus 14 squared, which is a 196. And this will be 14 times the square root of 4. Square root of 4 is a 2. 14 times 2 is also a 28. So we have that f of 2 does equal f of 14. And therefore the condition 3 holds true. All 3 conditions hold true. Rolle's theorem does apply here. Rolle's theorem says that the derivative evaluated at some value c, the slope of the tangent line, at some value c, equals the slope of the secant line connecting the two endpoints, f of b minus f of a over b minus a, for the mean value theorem. For Rolle's theorem, f of a and f of b are the same, so this subtraction here is equal to a 0 due to the third condition on Rolle's theorem. So Rolle's theorem says the slope of the tangent line at some value c equals to 0, where c will be in the open interval 2 to 14. Now we're guaranteed there will be at least one c, perhaps more, that'll be in that interval. We're going to find the one c or maybe multiple c's that are in that, where the slope of the tangent line is a 0. Now the left side of the equation, f prime of c, is evaluated by plugging c into the derivative. Now we can use any version of the derivative that we found up above, but we will use the simplified version here. So 200 minus 2c squared divided by the square root of 200 minus c squared equals to 0. We can now multiply both sides by the square root of 200 minus c squared, and on the right side, since it's a 0, it'll stay a 0. And so on the left side it'll cancel, on the right side it'll stay 0, and we're just left with the numerator equals to 0. We can now factor a 2 out of the numerator, leaving behind a 100 minus c squared equals to 0. And 100 minus c squared is a difference of squares, and can factor into 10 plus c and 10 minus c equals to 0. And that means we have c being able to be negative 10 or positive 10. We're guaranteed at least one c in this interval. We're going to want to determine whether both or maybe just one of them are in that interval by looking at how they compare to the interval. Well, the first one, negative 10, is not between 2 and 14. So the first one is not going to be included. The second one, c equals 10, is between 2 and 14. We will keep that one. And there is the value of c that satisfies the conclusion of Rolle's theorem for this function.